And as I promised, so this again, this will take, we'll allocate to this talk another sort of 45 minutes. And then 2 more talks. And as I said, we'll be going deeper and deeper into the math. So this will be a little bit more mathy, and then it will be even mathier and even mathier. Okay, so let's see who stays to the end. And this is based on a talk I gave at something called the PCP Fest. So PCP stands for Probabilistically Checkable Proofs, and I think you heard a lot about them in the past few days. So anyways, that's going to be the next talk, about what is the connection between probabilistically checkable proofs and these things that we call zero-knowledge STARKs. And this talk is going to have 3 parts. I'm going to talk to you a little bit, tell you a little bit about crypto proofs, which you all know about because you've been in this conference for a while. But you know what, maybe the takeaway is like yet another way to try and describe what these things are to your mom and dad. The second part is going to be the part with the acronyms, right? All talks must have them. In our case, we're going to explain what PCP, IOP, STIC, STARK, and FRI are, and then I'll list a few concrete math questions. Okay, so integrity in the dictionary is defined to be the quality of being honest. And by extension, computational integrity could be defined as the quality of a computation being executed honestly and correctly. So basically, the proofs we're giving are proofs of computational integrity. So here's an old proof of computational integrity, which you probably recognize, or the older ones among you might recognize it because now it would be, printed by a computer. But this is really a statement, or this is really a proof of computational integrity. So the statement that is asserted here is that the customer should pay $138.16, right? And what you have here is a proof of computational integrity. The prover is the party that generates this proof. So in this case, it would be the restaurant owner or the grocer if this was a grocery list. And the verifier is the party checking the computation. In this case, it would be the customer. So next time you're asked, what is a zero-knowledge proof and what are these proofs? You could say, well, it's just like a grocery receipt because it really serves the same functional purpose, okay? But of course, we wouldn't be, Bar-Ilan wouldn't be running a 5-day school on grocery receipts. So there's a little bit more to them. So in general, first of all, a general computational integrity statement. So this is a statement about summation of numbers, right? But a general computational integrity statement could be specified by a computer program that doesn't have to be summation. It could be something much more complicated, like verifying, all transactions in Bitcoin's blockchain. It would be specified also by a public input, like let's say the very first, the beginning of the network. There'll be some auxiliary private input, maybe it's all of the blockchain, and there'll be an output that could be, let's say, the hash of the latest block in Bitcoin's blockchain, and there'll be a specification of the amount of time steps it took to verify. So a general computational integrity statement is really a quadruple: program, input, output, and time that it takes. And the language of all of these statements, so Alon Rosen called it the universal language. It goes by other names. Sylvie Micali called it the computational soundness language. I'll call it the computational integrity language. It's the set of all quadruples that are correct. Computation starting from point A, reaching point B, with auxiliary non-deterministic data C and time T. Okay. So again, these receipts are examples of proofs of computational integrity. And the way you verify them is by replaying the computation. So today, when you get a computerized proof, you trust it. You wouldn't doubt that the summation is done correctly. But of course, in the good old days, I'm old enough to remember those days, you would actually do all kinds of checks or maybe sum it up in your head if you had the ability to do it. And you would verify it by replaying the computation. And This kind of proof has a lot of benefits. It's completely deterministic, it's error-free, and it's a one-shot, non-interactive statement. You can walk around with it, and everyone can verify it. So it's really great. The kind of proofs that we heard about these past few days are very different. They actually require randomness. That's not a feature, that's a bug. Right? You would prefer them to be deterministic. They also have an error. Again, it's a bug, it's not a feature. You would prefer them not to have any error. And they require interaction, at least in certain forms. You know, you could maybe try to remove it later on. So they are not as good in these respects compared to the good old proofs. But of course, you get a lot in return for slackening the definition. So here's a partial list of acronyms that probably you know to open many and most, if not all of them. So there's interactive proofs, zero-knowledge proofs, computationally sound, probabilistically checkable proofs, multi-prover interactive proofs, interactive probabilistically checkable proofs, linear PCPs, probabilistically checkable proofs, interactive proofs, and IOPs. And that's just a partial list. A large number of different models and associated with them are very deep and beautiful math and crypto results, okay? But if you lump them all together and think of them as sort of, proofs involving randomness, interaction, and cryptography, you get a lot of benefits. The one thing, which is the title of this week's school, is that of privacy. You get zero knowledge. You can preserve the private inputs of the prover, right? As in so, right? It's a little bit like you could sort of blacken out some parts of the proof and still get the same guarantees that the answer is correct, right? And that's very magical. So that's the zero-knowledge aspect of these proofs. You can also get scalability, and now I want to define it a little bit more formally. So when I say scalability, I mean the following thing, that if you fix your language or computation and you let t go to infinity, t is the number of cycles or the running time, you need two things to happen simultaneously for it to be a scalable system. One is you need the proofs to be generated in quasi-linear time in t. That means t times poly log t. And simultaneously, you need the proofs to be verifiable in time poly log t cycles, okay? So, and it looks roughly like this. So for a computation, that's the black line that takes time t. You need your prover to scale like t polylog t. This is t log t squared. And you need the proofs to be verifiable in something that looks like polynomial in log t. Okay? So that's scalability. And you can get such proofs. And that's what we mean by scalable. Universality or Turing completeness means that they apply to any computation C. I should qualify that and actually say that the most you can hope for with these proofs is to apply to any language in non-deterministic exponential time, or in NEXP. Okay, so that's the definition for us for any computation, any reasonable computation C. And another thing is transparency. It is also known, or more famously known, as public random coins protocol or an Arthur Merlin protocol. I prefer the word transparent because it's one word as opposed to Arthur Merlin or public coins. And it also is a little bit easier to explain to my mom. If I tell her, oh, we just have this beautiful public coins protocol, it's not clear if public coins is something good or bad and how the coins are related. Maybe it's related to the blockchain. Transparency is something that captures the essence of what you get from public coins protocol, and it's a little bit more transparent than Arthur Merlin. Famously, you could use zero knowledge for things like Zcash shielded transactions. You can shield the payer, payee, and the payment amount. I didn't mention this, but I'm also one of the co-founders of, I'm a founding scientist of the Zcash company, and I very much like Zcash. But right now I'm more into STARKs than the ZK SNARKs used there, even though they're great as well. And you can also use zero knowledge to prove that you paid all your taxes without revealing them, and a whole bunch of other things they're really good for. And scalability examples, well, we just went into great detail in the previous talk about one particular scalability application of these kinds of proofs that specifically Starkware wants to bring into the world, so I won't go over that. Again, if you take just another example, just to bring in some numbers, suppose that, this is just, if the verifier time is log squared t, and prover time is t times log squared t, and let's suppose that it would take to verify all of Bitcoin's blockchain a peta number of cycles, 2 to the 50 steps, which is roughly what it should take. So a prover could run in time 2,500 times a peta, which is considerably more than a peta. It's 2,500 times more. So the prover would work more, but then everyone else could verify the validity and computational integrity of the whole blockchain in 2,500 steps, which is much less than 2 to the 50. So that's the kind of thing you could get with scalability. And of course, you could help solve scalability problems. We spoke about this. Okay. So before I was chief scientist at Starkware, I was a researcher at Technion, and the TLDR of my research, in hindsight, it wasn't evident back in the day, was that of sort of transforming a certain kind of basically scalable and transparent zero-knowledge proofs from something that was known as a galactic kind of algorithm, things that work asymptotically well when t goes to infinity, but not for any t that is smaller than the number of atoms in the universe times the number of nanoseconds till the sun cools down, to something that actually could work, say, on this laptop and produce some meaningful stuff. So again, this is something that in hindsight, I embarked on this research in 2001, unbeknownst to me. I was just interested in understanding this very beautiful math behind the probabilistically checkable proof theorem. But 18 years later, looking back, that's where this path led me, to things that are more and more applied into starting companies and stuff. And of course, it's been a long and fun journey with many, many, many amazing peers and colleagues. If I read the whole list, I'll end the time. But this is an ongoing, really interesting effort. So there are many, many flavors of proof systems based on beautiful constructions. You heard a lot about them, the bilinear pairing ones, the linear PCPs, the ones based on secure multi-party computation, based on a whole bunch of proofs for muggles and IP. And over the past 5 years, or maybe 6 or 7 years, there was also a large number and growing number of beautiful implementations. Pinocchio, LibSNARK, You heard about Ligero, Hyrax, okay, a whole bunch of them. So, and there's this website that you're invited to go, and there's a very big list of resources there to be read. I want to focus on a very particular line of research that is part of this bigger family, okay? And that's the one that relies on the acronyms PCP, IOP, STIC, STARK, and FRI. Good. So we call an argument system, now here's a definition. We say that it's a ZK Stark if it satisfies several properties. First of all, if it's zero knowledge. If it's scalable according to the definition previously said, so for a certain language, as t goes to infinity, proving time is quasi-linear in t, t polylog t, and verifier time is polylogarithmic in t. Transparent. All the verifier messages are just public random coins, so there's no trusted setup in particular. An argument of knowledge means that if a prover interacts with a verifier and succeeds in convincing the verifier with high probability that the claim is correct, then there exists an efficient machine that can extract from that prover by resetting it and replaying it, can extract a witness that shows that this instance is in the language. Okay, so if you see a proof, the way to informally think about it is if you see a proof, you can actually extract from it. Yes, Jens? Great question. Good. So why pick scalable to be the The question is, why define scalable to be the combination of quasi-linear and polylogarithmic? Good. So I just want to point out that this is nearly up to polylog factors. This is optimal. Why? You can provably, you cannot have a prover that runs in less than t steps for general languages. So, okay, so we would like to say that, we would like to reach provers that run in t cycles or O of t cycles. We'll get to that in a minute. And here we're slackening a little bit. We're allowing the prover to be t times polylog t. And also you can prove that the verifier cannot, if you allow the prover running time t, the verifier cannot scale for general languages better than logarithm of t. Because if the verifier would run in less than log t steps, the prover who's allowed t steps could just sort of exhaustively search through all possible messages that the verifier would read and find something that satisfies it. So up to removing the exponents in the polylogs in these two things, you can't do any better. So another way of saying this would be nearly best possible. Now, why do we allow these slackness? The honest answer is that I don't believe that in my lifetime we will see a strictly linear prover in Boolean complexity. I mean, we already know of strictly linear provers if you allow, the group size or the field size to be polylog in T. But so I mean, one would say, well, that's really a polylog factor. So I'm saying I don't believe if we would have taken the definition of scalable to be strictly linear proving time, I don't believe that in my lifetime I would get to see it, unfortunately, because okay, never mind. I mean, I don't believe we'll see it in my lifetime. And I think also making the log strictly, exponent strictly 1, I also don't believe that I'll get to see it in my lifetime, the combination of those two. So that's why scalable is, I think, something that is still attainable. And it also captures the effect of scalability that I talked about in the previous talk that allows you, let's say in a permissionless blockchain, to actually scale because of this exponential gap. Yeah. So that's, but it's, it's just a term that captures, I mean, it could be replaced or it could be opened up to the definition and said, we want a proof system in which both quasi-linear time and polylogarithmic time, but I think it's, it captures the spirit of what the scalability offers. Yeah. Yes? Strictly linear Boolean complexity? No, arithmetic I agree. Arithmetic, I agree. But, yes. So that's a very good question. I think that communication, so there are cases where communication complexity is sufficient for various purposes, but the nice thing is that running time of the verifier is an upper bound on communication complexity, right? No. So okay. So again, the communication complexity cannot be less than log t. Why? Because a prover allotted time t would say, okay, there are only log t bits that this. Well, it depends if it's interactive or non-interactive. It maybe go down to log t. Let's not go there. But I mean, that's a discussion that we can take offline. It's a reasonable definition, I would say. But yes. Completely. Wait, first of all, the whole point of a definition is to define something and exclude some other thing. That's perfectly fine. When you say let F be a field, so, some things are a field and some things are not. For a second, I don't want it to be interpreted or thought that nothing but this version of scalability is what is important. Hell no. There are other forms that are extremely important and beautiful and meaningful. we want to brag about our work, so we use this definition. No one should be offended or think that, oops, sorry, that other forms are not important or not useful. Yes, okay. Okay, so I just want to say that there are actually, for those who want to play with them, so STARKs can be interactive, and this could actually, in certain settings, be something useful. For instance, you could use the blockchain for the source of randomness, and there are some benefits to it. You heard about the Fiat-Shamir heuristic and the fact that it can be used in these settings, so you can also make it non-interactive. And I just want to say that you also have actually STARK implementations to play with. So the first one is called SciPOC. You can search for it on GitHub, and the second one, which actually also has zero knowledge, is libstark, and you can search for it as well. So there's stuff to play with for those who like it. So a little bit more about the math. I just want to see how we're doing in terms of time. So I want to finish at the... okay, good. So all of this polylogarithmic verification goes back to the very early days of PCPs, to this marvelous work by Babai et al. And here's a quote from them that is, we often use. In this setup, they wrote, so this is Babai, Fortnow, and Levin in 1991. I now see that I'm missing Szegedy, so it's actually BFLS. Babai, Fortnow, Levin, and Szegedy, 91, wrote this. In this setup, a single PC, reliable PC, can monitor the operation of a herd of supercomputers working with possibly extremely powerful but unreliable software and untested hardware. This was before Bitcoin, right? And what is this beautiful setup? It is the setup of the PCP theorem. Oops. So what is it? The setup is like this. So to prove that X belongs to language L, we're starting with the math, for some non-deterministic language, the verifier, we assume it has oracle access to another string, pi. That's the PCP proof. And the verifier now is going to run in time that is polynomial in the size of the instance and in the logarithm of T of n. And we want it to be the case that if X is in L, there exists some proof that is accepted with probability 1, whereas if X is not in L, then all proofs are rejected with probability half. And amazingly, since the early and mid-1990s, constructions of such systems were known. This is the setup. If you give oracle access to this proof, you can distinguish between truisms and falsities with a very small number of queries, where actually the number of queries depends only on the error you want to tolerate and not on n, which is an amazing result. Okay. So this is an unrealistic model that you have oracle access to this proof. The way to realize it, and again, this was discussed in one of Bloom's talks, is to use Killian's method of applying a Merkle tree or some commitment to the bits of the proof, sending that as the commitment, getting queries, and opening up the entries and proving that they are consistent with the Merkle tree. Okay? So that's how you realize it, and then it gets transformed from a proof into an argument system because it works only for computationally bounded proofs. Okay. A little bit about scalability and PCPs. So the scalability effect will come from the exponential decrease in verification time, and the larger this decrease, the bigger the scalability effect. So in 1995 already, we knew that you could get this exponential gap between naive verification time and PCP-based verification time, which is really great. But why hasn't this implemented since 1995? Part of the reason is that, first of all, the verifier complexity was pretty large. But more importantly, the proving time to generate a proof scaled polynomially with the length t. It wasn't yet a scalable, only the verifier was polylogarithmic, but the prover in the early works was still polynomial. So there is a limit to the amount of computational resources in the world, and it wasn't enough to implement, in 1995, the proofs in order to gain any meaningful scalability factor for computations of interest. And you know, as I said, a lot of my research has been about improving, you know, getting things like quasi-linear proving time along with polylogarithmic verification. So this was around, you know, 2006. We knew to do things a little bit more efficiently, but still the exponents in the polynomials of the logarithm were kind of large. And part of it was due to the kind of model that we used. And the model is this PCP model, which is really great, but still not efficient enough. So we need to move, or we wanted to move to a different model that is even more efficient when you think about concrete applications. And that is the model called the interactive oracle proofs model. It was suggested independently in work of Reingold, Rothblum, and also in work of myself with Chiesa and Spooner. And the setup, it's like a multi-round PCP. That's the model. So instead of just giving oracle access to a proof, in the IOP model, the prover gives access to a proof, but then the verifier sends random coins, and now the prover replies with another part of this oracle proof. So another chunk, a big message to which you have oracle access. And the verifier again tosses coins, and again there's another chunk of the proof. And the chunks don't have to go down in size. I mean, you know, in many applications they do, and 2 talks later I'll show you a case where they do go down in size, but they could go up in size, they could be the same size. The main thing is that we allow many rounds of creating of the oracle. And that's the IOP model. So it's like a multi-round version of the PCP model. And it turns out that in this model, okay, you still allow the verifier, you limit the verifier running time to be polylogarithmic, and you want to count the number of queries to be small. You would like it to be the case that if X is in the language, there is a sequence of proofs that are generated in response to the verifier randomness that always satisfy the verifier. And you would want it to be the case that if X is not in the language, any sequence of such proofs will not manage to satisfy the verifier with more than probability 1/2. So this is the definition of an IOP. And again, the IOP is an unrealistic model because it's not clear how do we manage these IOPs and, you know, how do we give oracle access to them in the world, let's say, of blockchains or the internet. And the solution is to transform them using an analog of the method of Killian, but sort of in an interactive way, to generate these Merkle trees and commitments and open them. And if you do that to an IOP, you get, this is one way of constructing ZK STARKs. I just want to say that any other method of constructing a system that has the properties of a ZK STARK is also a ZK STARK. But this is the approach that we took. But there should be other ways of doing it. And I encourage you to do these things. So why move from a PCP model to the IOP model? And the answer is that with IOPs, there are many results that we can prove that we don't know yet how to prove in the PCP model. So both theoretical results and practical results. For instance, we know to build a 2-round IOP that has perfect zero knowledge and a non-adaptive verifier for NP. So this is a question I was introduced to by the great Yuval Ishai, among many other things in cryptography that he taught me. So in the PCP world, we still don't know how to, right? I mean, I think it's still, at least since till the time I left academia, it was still unresolved. In the PCP model, we don't know how to get a ZK PCP with 1 round or a 1-round IOP with these properties, but we can get it in a 2-round IOP. You also get doubly efficient and constant round interactive proofs. That's the original setting that Reingold et al. Introduced the IOP model for, and a whole bunch of other theoretical results. You can also get very efficient constructions in practice. So what you get is from running times that look roughly like this, you get something pictorially that looks a little bit more like this. So instead of having the prover run in very large quasi-linear time and the verifier run in very large polylogarithmic time, you get things that are a little bit smaller, and that's another reason. So I just want to show you some numbers. This is already from a month ago, so this is from this little thingamajig quad-core, Lenovo laptop. If you focus in, so this is for repeated invocation of Peterson hashes. I don't think you can see very well here, but the prover time is roughly, this is for 8,000 invocations. It takes 72 seconds, and verifying it takes 15 milliseconds, which means that naive verification of 8,000 Peterson hashes would take you 1.6 seconds or 10 times more. So this just shows that, this is just some plotting of some numbers that show that we can already go through the scalability threshold with even on reasonable sized machines. And again, the numbers are probably going to go down a little bit more. So the way we actually, most of the work when we build a Stark is not in the application of the Merkle trees and the Fiat-Shamir heuristic. Most of the work is pure information theoretic, math, algebraic complexity in the world of the IOP model. So there's no cryptography involved at that phase. Only at the very end we apply the Fiat-Shamir heuristic and random oracle model in order to make it a realized system. So I want to give you some definition of one of the things we try to build. So this is a scalable, transparent IOP of knowledge. And we say that a proof system, an IOP, for a language L, is said to be scalable if proving time is quasi-linear and verifying time is polylogarithmic. Transparent, you already know, if it's an Arthur Merlin protocol. And it's an IOP of knowledge if there exists an extractor that extracts in polynomial time in T of n, a witness of membership from a good prover. So this is a definition of a stick, and most of the work that we do is trying to improve our understanding of sticks, and then we just plug in hashes and whatnot to get them to be a Stark. Now you can also talk about a strictly scalable stick, so this is another invented definition. If the proving time is strictly quasi-linear, it's O of T of n log T of n, and verifying time is O of log n. And I just want to say that we have this recent result that if you measure things in the arithmetic complexity and the field size is large enough, then you can actually get a strict zero-knowledge stick according to this definition in the IOP model. But the caveat is that you're using arithmetic complexity over a field of size O of T of n. Okay, so this is a result that we hope to post soon. It's joint work with Alessandro, Lior Goldberg, Tom Gur, Michael Yaptsev, and Nick Spooner. And I think this is a great open question that I can say a lot more about. Can we get a strict stick in Boolean complexity? I think the answer to that goes through efficient AG codes. I'll say a little bit more about that. So there's an associated object that's called an IOP of proximity, which is the analog of a PCP of proximity. And there, the object or the objective is not to prove membership in a language, but rather to prove that a function is close in Hamming distance to some code. Typically, it's something like the Reed-Solomon code. So in this case, we assume that we have Oracle access to a function, and we would like our verifier to be able to distinguish between two extreme cases. The good case is that f is a low-degree polynomial, evaluation of a low-degree polynomial, and the bad case is that it is far in Hamming distance from every evaluation of a low-degree polynomial. And for that, we could have the code that often interests us is the Reed-Solomon code, comprised of evaluations of low-degree polynomials. And the very last talk I'll give will go into detail about the Fry protocol that is a specific IOP of proximity for this problem. And it has really, really good parameters. The proving time is 6 times n arithmetic operations. The verifying time is strictly logarithmic in the block length of the code. And the rejection probability scales very well. So for a function that is delta far from the code, the rejection probability is at least delta. Originally, we proved it for very small deltas. Then we improved it to slightly higher functions of delta. And just like 2 days ago, we submitted to CCC an improved analysis that shows a tight bound that it is up to the cubed root of the rate, 1 minus the cubed root of the rate. It looks something like this. So as your rate goes to 0, this direction, the rejection probability of words that are delta far are rejected with probability delta that goes up and up. The green line is the upper bound, and we have reached sort of the Johnson bound in a different protocol. And of course, the question of this soundness is one of great interest. I just want to say I'm going over this part pretty fast because the very last part of my talk, the very last talk, will be focused only on Fry and the Reed-Solomon proximity problem. So we'll talk about that in great detail. So I just want to finish this part of so this is the second talk. I want to just mention some concrete questions. Can you construct a strict stick for interesting languages that are in non-deterministic polynomial time or exponential time? And one approach to do it would be to use algebraic geometry codes that are generalizations of low-degree polynomials. But this would require, at the very least, quasi-linear encoding time for AG codes, which is something that is not known and is of interest, generally speaking. Can you get better soundness analysis for Fry? So this will be the topic of the very last talk, and we have some exciting improvements that I want to share with you there. And the last one is that of improving soundness even below what's called the sliding scale conjecture for IOPs and sticks. Currently, the soundness error bound is always at least the rate of the Reed-Solomon codes that we operate with. But I believe that there should be protocols that give you much better soundness error, much smaller soundness error that are polynomial in 1 over the field size. And this would lead, if we find such things, this would lead to even shorter communication complexity for things like STARKs, but also for other protocols like Ligero and Aurora that also use similar techniques. Another class of questions, which is a little bit more security related, is can you come up with a family of Stark-friendly crypto primitives? Because if you want to argue about invocations of things like SHA, you're looking at very large cost of roughly the order of 10 to the 4. Peterson, proving things about Peterson costs roughly on the order of thousands of constraints. If you go to things that are more efficient like MIMC or the recent Jarvis and Friday codes, you're already in the hundreds of things. And the question is, how low can you get? Because as you decrease this complexity, you're hitting across bounds of algebraic cryptanalysis, things like the Grebner basis algorithm. So it's a very interesting question to understand there. There's also the question of Stark and stick security analysis. And can you throw away the Merkle trees and use some kind of different accumulator-based system to record those proofs? And of course, there's very beautiful recent work by a bunch of cryptographers on this, and it's a very interesting and meaningful question. The last one, of course, that is of great importance is how do you know that a stick or a Stark or a SNARK or one of these systems actually captures correctly the computation that you want to argue about? And this is very important in the context of cryptocurrencies because they will carry a lot of value, so you better have the right thing. Again, I just want to repeat, Starkware is hiring, and we will have a dedicated workshop in which not only I will speak, but some of our very talented scientists and engineers. So please sign up to that as well. It will be held, the first one will be held up here in Israel, so please do that. That's it.